Starting as I usually do with Chuck Penson's excellent book on Heathkit test equipment products, I'm flipping to the capacitor section, and Heathkit's first version of this instrument was the CT1, which came out in 1957, and they made for about 5 years up until 1962 at the whopping price of about $8, which of course was a lot more back then. Still a very affordable price at the time. As it says here, based on the number of these seen online at Hamfests, Heath must have sold tens of thousands of these. It uses an electron ray indicator magic eye tube in a clever circuit that uses a transformer power supply but no rectification, and built into the same cabinet as the early Heathkit VTVMs. It checks open and short, and also tests for intermittent capacitors. It is an in-circuit tester and will detect open caps from about 50 picofarads and up, provided they are not shunted by an excessively low resistance, shunted by more than 2 kiloohms at 50 picofarads or 400 ohms at 100 picofarads, 30 ohms at 30 ohms at 300 picofarads. Okay, yeah, so it's shunted by lower resistances at higher picofarad values. It will detect shorted caps up to about 20 picofarads not shunted by less than 10 ohms. The test frequencies are 60 Hertz for open for short tests and 19 megahertz for open tests. And it was replaced by the IT-22, which is the one shown in this video. This one came out in 1962 and continued for about 4 years until 1966. Restyled, but otherwise identical to the earlier model. This particular instrument belongs to a friend of mine, and he handed it over to me with the understanding I would fix it up and return it. And as such, I wasn't originally planning on doing a documentary video on it, and I just took a few pictures. But now that I am doing a documentary video, I'm going to show this portion of it as a narrated slideshow. So this is the way the instrument originally came. It had been in storage for a long time. The front of the magic eye tube at the top of the picture here was very foggy, and I think it was just layers of crud on it. I don't know how it got so cruddy. There's a lot of paint damage at the left center. The knob and the terminals are just thick with crud, so obviously a lot of cleanup is required. Looking around the back, the case has got a lot of dirt in various spots. The power cord was absolutely filthy, although serviceable. And the original strain relief was either never installed or was removed for some reason, and just the cord is exposed to the raw metal edges of the hole there. All things I want to remedy. So here are some internal views I took. This is the right side, and the tube is just held in a spring clip, and it can be adjusted forwards or backwards or rotated slightly for best appearance. And the power cord and associated power wiring is on this terminal at the front of the image. The oscillator auto transformer is this cylindrical item sort of near the middle of the picture with an open center. And let's see, there's a few other odds and ends, some resistors and things visible on this side, and the power transformer is down there on the bottom. Going around the rear, we once again see the rear bracket, most of which is normally hidden by the case. Just the power cord entry is there, and we see the socket for the tube up at the top. Considering there's fairly high voltage on there, it's a little bit exposed, but of course if the case is closed, then it isn't. And you can see the side of the power transformer at the bottom of the image. And here's what would be the left side if we were referencing it from the front. We see the other side of the magic eye tube at the top and its cable. all the wiring goes to a 5-position terminal board on the top of the chassis bracket. There's also a large capacitor there and some resistors. And then there's a smaller 3-terminal terminal board at the bottom of the bracket, which has some more wiring on it and a couple more resistors. And that's really about it. Very few components on this circuit. Before proceeding with cleanup, I wanted to make sure that the circuit was basically functional, especially that the Magic Eye tube was working. So here's just a few pictures, and here's with the tube in its so-called open position with a wide wedge at the bottom. That's called the shadow. And then here is with the tube closed down to its closed position, just a very narrow wedge at the bottom. So I pulled the knob and the terminals off and soaked them, and also soaked the rear of the case in warm soapy water and then brushed them off and rinsed them. Here are the knob and the terminals spotlessly clean. And I cleaned up the front panel and also touched up the paint where it was boogered up. I thought I had it at the right shade. I know that this paint I use usually gets a little darker with the matte finish paints and when it dries, but this one didn't, so it's still better looking than it was before. I found a strain relief similar to what was probably there originally, and I had to modify the hole slightly with my Dremel tool to make it fit. I took the power cord off and went over it over and over with a wet rag, and even cleaned the groove between the two zip halves. Got it nice and clean. But to do that, I had to remove it from the meter, so I just cut it off and then cleaned it and then reinstalled it with the strain relief. And here's with the new wire sticking in and the remnants of the old wire hanging down. And then I re-terminated the new wire where the old one had been. I used several different solvents, from isopropyl alcohol to a little bit of acetone on a Q-tip to mineral spirits, and nothing seemed to be removing the crud that was on the front of the tube. I'm assuming it was supposed to be clear originally instead of frosted. Maybe the gunk was actually the deteriorated remnants of a frosted finish, but I decided to clean it up, so I put a buffing wheel on my Dremel tool and went over it and got it to look like this. And as far as I can tell, it does not make the product work any worse, and certainly looks better than it would be if I hadn't cleaned it up. By the way, the Magic Eye tube here is a type 1629, a very common type that was used in old radios, old test equipment, all sorts of things, and still quite a few of them available as new old stock today. Okay, cleanup, restoration to the degree that I did it. I didn't change any components, just viewed from different angles. It's much cleaner and better looking now. I wish I could have done a little better on the touch-up paint. Fairly good looking instrument considering its age. Okay, let's let the camera adjust to this. Maybe it won't. There we go. That's with the eye open. And I have a capacitor hooked up here. It's in the short check position. When I turn it to the spring return position for testing, if it stays open, then it's going to indicate a short. If it closes, then it's going to mean it's okay in regards to shorting. So let's get this guy back so it's exposing. I'm turning it to test, and it closes up. So that means it is not shorted. Now I'm going to turn it to the open check position, and the eye is currently closed in that position. It'll stay closed when I turn it to the test position if everything's okay. So really in both these cases, the eye closed means it's okay for that test, and the eye open means it's not. So I'm going to turn it to the test for opens position, and the eye remains closed. That means it is okay. It is not an open capacitor. Now what if I disconnect one side and do the open test? The eye opens. That does mean that the capacitor is open. But it'll take a while to close up with nothing connected. I've found that when I do these blatant things like really disconnecting the capacitor and then doing an open check, the eye returns to sort of a half open, half closed position, and I have to return the switch to the AC off position to get it to reset, like it has here. So now I'm going to do the short test again, and it closes up like it should and returns to open. But if I actually short it out, and I'm going to do this with a jumper instead of shorting the test leads together. Now when I do the short test, the eye remains open, indicating that the capacitor is shorted. If I remove the short and redo the test, now the eye closes. That's about what this guy does. Let's just take a quick look at the manual. I don't think they really did any updates to the manual since the 50s when this meter first came out, even though they've re-released it as the IT-22. I think they did minimal updates. And as such, it's not as sophisticated or as thorough as the later manuals that were very famous for Heathkit, or for which Heathkit was very famous. This particular one is copyright 1962, but that may just be because they had to update the artwork here. In other ways, it may be identical to the old version. So we just have a picture of the front of it. We have some brief specifications. I don't know if the original schematic appeared here, but probably it did. This is a modified manual I got. It was originally from manualman.com, but I've made some additions and modifications to it and rebound it with a wire binding. The original binding was a very tight comb binding that the pages were binding on. Anyway, so brief introduction, circuit description, that's all there is, just right there, a circuit description. It's not very thorough. I'm going to go into a little bit more detail in this video. Then we're into proper soldering procedure, some chassis views and step-by-step chassis assembly, some basic wiring. All wiring is point-to-point on this. There are very few components. Adequate diagrams, but not as thorough as you would have seen on later manuals. Still pretty good. And their pictorials are not as cleanly drawn. The 3D views are a little primitive compared to the way they drew things later, but still perfectly adequate for the task. And then we get into the, in case of difficulty, very brief section. The operation, this is the whole thing right here. There's not much to operating it. A bit of a curiosity here that the manual here describes putting on a separate pointer to the knob, and yet, well, actually this one does. Some other pictures do not have the pointer. And just have a line on the knob. So I think they must have had some variation between versions. And then we have a whole section on service and sending it in for repairs, or if you can't get it to work. Shipping instructions. There's a parts list, a bit on the bibliography and warranty. I don't usually see a bibliography in Heathkit manuals. It's kind of interesting. So they, refer you to some books where you can learn more about this kind of thing. And then a final chassis photo, and then an enlarged schematic. I think that's just something that manualman.com did. And then an order form for ordering parts. And that's where the original manual from Manual Man ends. And then in my rebound version, I wrote my own, what I'd consider a complete document. And it just pretty much has everything I learned studying the circuit and playing with it. Beefed up specifications, a more detailed operations section, pointing out some of the caveats. A little better than Heathkit did originally. And then how to test the instrument to make sure it's working correctly. And then I have diagrams that I'm going to show in this video, and various markups that I did while studying the circuit, all bound together, but that's not something anybody else is likely to see, unless I decide to publish the PDF. Okay, this particular circuit exceeds my expertise with vacuum tube circuits and vacuum tube oscillators in particular, so it's a little bit watered down here. This pictures a form of what's known as a Hartley oscillator, which I had to look up. Apparently it was invented around 1915 by a guy named Ralph Hartley, hence the name Hartley oscillator, who was a researcher for Western Electric Company. And then a few years later, he used this and worked with it when working for Bell Systems on doing some research associated with the transatlantic radio telephone system that they were looking into. I think that was done shortly before 1920. So, in its common form, there will be some sort of a vacuum tube equivalent to a triode. It can be an FET these days, or bipolar transistors, or all sorts of different things. I think the vacuum tubes he was working with weren't exactly triodes, but something that could be used in an equivalent way to what we're familiar with as triode tubes these days. There's a power source, and it's applied to the plate of the triode, and then there's a grid, and then there's a cathode, and the cathode is the output of the tube, so current is flowing in this direction, and then it goes through a coil and then back to the power, in this case ground. There is an additional winding on here, like an auto transformer, so additional voltage is developed in this part of the coil, and then that's coupled back to the grid, and that sets up an oscillation. I don't want to go into it much further than that because I'd be dealing far outside my area of expertise on this type of circuit. Using a tube with a true triode functionality, though, that can have a sort of a built-in rectifier effect. And normally this would be a DC circuit, but in this implementation in the Heathkit IT-22, it's just using a winding off of the power transformer, reference to ground. In the case of the Heathkit, it's 540 volts, which surprised me because the tube in question, the 1629, as far as I can tell from its data sheet, is only rated for maybe 250 volts or something. Of course, this is going to be sort of halfway rectified. I don't know if that factors into it. The design here is taking into account that connected this way, the tube only conducts in this direction. So it's like it has its own built-in diode or rectifier, with the cathode being down here. So current only flows out of the transformer in this direction and can't flow the other way. So in that sense, it's only getting half the voltage. You know, even then it seems like it's excessively high. But apparently it's okay, or maybe the spec sheet I have is erroneous. Anyway, so this is the crux of the oscillator. I said earlier that usually there's a capacitor in parallel with some or all of this winding, at least in the old diagrams I've looked at. In this case, the capacitance seems to be in series with this part of the coil, and this whole thing is considered to be part of the primary. So you've got an oscillator, and it's called the Hartley oscillator, and according to the Heathkit manual, it should be running somewhere around 19 megahertz. There's also another part to this winding. If you treat the ground here as a tap, there's more to the winding on this side, and that delivers an additional 55 volts, which is used for biasing in some configurations of the circuit. Right here I've just shown it doing nothing. Then there is another secondary which produces 6.3 volts for the filament of the 1629 vacuum tube. So this is an elaboration of the previous schematic, and I have it drawn to reflect the short check configuration. In other words, it's when the instrument is set up to check for shorts, and it's in sort of the pre-check configuration, not the actual test configuration. So what's different? Well, first off, there's more to the vacuum tube. This is actually a electron ray tube, the 1659 or 1629. The way I had it drawn before left off the target part. So we still have the cathode, we still have the grid, we still have the plate, but now there's an extended plate, and there's also a target. At least that's what it's called on the data sheets. The target is what's directly energized from the high voltage, and then through a resistor with a capacitor to ground develops a somewhat lower voltage here, which is applied to the plate. So higher voltage here, somewhat lower voltage here. I haven't done the math, I don't know how much lower. Let's see. So you still have the rectification, built-in rectification going on, so still the current can only go in this direction. And you still have the Hartley oscillator built out of this triode part going back in here. You've still got the transformer here going up, but it's not tied to the grid in this configuration. Instead, it's tied back to a secondary winding on this transformer, or this coil, which by the way does not have an iron core, it's just an air core. And it's running at a pretty high frequency. It should have decent efficiency, I suppose. There is a capacitor and a coil in parallel, and then a series capacitor. In this instance, this point is wired back to the capacitor going to this coil, and also there's a 3.3K resistor to ground. And then the grid, even though it has a 2.2 meg resistor going to ground all the time, in this configuration it's also shorted out, so this is negligible, or it's irrelevant. The grid is essentially just tied to ground here. And let's see, we're not doing anything different with the high voltage supply. So this tube is being told to do essentially nothing, it looks like, and we're not doing any kind of a feedback. So with this part of the tube engaged, if there's a lot of current flowing in this path, then the electron ray part of it ends up painting a picture on the front of the tube that looks like this. It's the open configuration, and it looks like a big pie slice has been cut out. Everything else here is illuminated and this part will be dark. That's when you get high current through the tube. If you have a lower current, then that progressively closes down till you have just a sliver. It almost looks like just a little line that isn't lit up. So that's the low current configuration. So I think what's happening here, again I'm not positive, but I think if you have the grid completely shorted out, it's going to result in no control and you're going to have a lot of current flowing. And that should cause the tube to display like this. And I think even though the manual doesn't describe it, when the instrument is in the check position, in this case the check for verifying short circuits, it's setting up most of the circuit the way it's going to be for the actual test, but it'll be a little bit different so that you get verification that the tube is working properly. And so this is what you should get in this configuration, is the wide open, and that's marked on the front panel of the instrument as being the desired display for being in the check position. I'm not sure that this stuff here is doing anything in this configuration, since the grid is grounded and the current is going to flow this way anyhow. What this stuff is doing here, I'm not really sure it's doing anything really, or nothing important. That's my guess, but again I'm not positive. Here the drawing is reconfigured slightly, so what I'm calling the short test configuration. It's almost the same thing, except here, I guess I should mark that with a dot, the short circuit on the grid is removed, so now we have this 2.2 meg resistor in effect, and it's also connected to something else. In addition, this part of the circuit's essentially the same. We have the oscillator tied back to here, and then there's a resistor to ground, 3.3K. Another thing we're doing is we're tapping off that 55 volt transformer secondary and going through a limiter RC arrangement here, and then connecting it to the grid and also to the red terminal on the front. The black terminal is grounded, and then there's this 1.5K resistor to ground. So you have your capacitor under test out here, like that, CX, the capacitor under test. So apparently what's happening here is this transformer is applied as a biasing voltage to the grid of the tube. Already mentioned that. The test leads are connected to the capacitor under test, which is essentially putting it between the grid of the tube and ground. If the capacitor under test is shorted, and we are after all doing a short test, testing for a short in the capacitor in other words, if it's shorted, it's doing essentially the same thing we had before. The grid is shorted, therefore you'll have a high current through the tube, and the tube will display the wide open pattern, which is identified on the front panel of the instrument as a shorted condition. However, if you don't have a shorted capacitor out here, in other words, if the test capacitor is not shorted, it will have no effect on the biasing voltage. So you've got this biasing voltage coming in here. This capacitor isn't having much effect, if any, on it, and the biasing voltage is applied to here, well, it biases the tube and it results in a lower current. Therefore, the image on the tube closes down, and that's how you get the closed image, which is identified pictorially on the front of the instrument as being an OK test result. So that seems fairly simple. And it doesn't seem to require the feedback. In other words, I don't think that the Hartley oscillator is even working in this case. We have some rectification, and we have current flowing through this coil here, but the way it's tied back to essentially nothing that would influence any other part of the circuit, and because it's not tied back as a feedback signal, it's not self-biasing, it's only biased by this lower frequency, 60 Hertz signal coming off this transformer winding. I do not believe it's operating as a Hartley oscillator. It doesn't seem like it could be. But the way I've described it, I think makes sense. Okay, now for the configuration that checks for an open capacitor. In the check position, which again I think is just there to validate instrument functionality for that configuration, instead of biasing the grid of the tube from the 55 volt winding on the power transformer, the Hartley oscillator is allowed to function normally. So the grid comes from the feedback from the Hartley oscillator. And as long as we have that going, you're going to get some degree of flow through the tube. If you introduce this secondary winding, it's always there, but it's often configured in a way where it doesn't really have much effect on what's going on here. If we have a short circuit down to here, it's kind of like if we have a short circuit here. It sets this part of it up in such a way that it renders the functionality of this part largely ineffectual on this part. So you get a moderated amount of current flowing through here. You know, it's not zero, but it's a much lower amount than it might otherwise be. And when the tube has a lower current going through it, you get this kind of an image, the closed down tube image. And that is indeed what the front panel of the instrument says you should get when you're in the open check position. Now when we switch to the open test, the only thing it really does is it removes the ground that was here. So we're not simulating a grounded capacitor, or a shorted capacitor rather. So we have the capacitor under test here, and it's going to have some amount of capacitive reactance back to ground. And that influences how this circuit is working. At the frequency we're operating here, around 19 megahertz with the Hartley oscillator, the reactance on this will be low enough that it looks a lot like that short circuit we had before, and it reduces the effectiveness of this circuit enough that the oscillator can run pretty much normally, and thereby moderating the current going through the tube, and therefore it's going to have the closed down pattern. And the front of the instrument says when you have that and you're in the test position, that indicates that the capacitor is okay in regards to whether it's open or not. However, if the capacitor here, oh by the way, if you have a short circuit here instead of a functioning capacitor, it'll act just like when we had the ground here in the check position of the switch, and that's going to have the same result. You're going to have the closed down look on the tube. However, when in the test position, if you in fact have an open circuit here, the capacitor is open or it's not connected or whatever, now that allows this circuit here to operate in a way that's much more influential on what's going on here, and it actually, well, it's essentially stealing energy from this coil to the point where it shuts down the oscillation. It prevents oscillation of the Hartley oscillator. And with that, then there's no moderation of the current flow, and you have a lot of current flow in this direction through the tube. And we know from previous discussion, when you have a lot of current flow, the image on the tube opens up into the big pie slice, and that's marked on the front of the instrument as indicating an open capacitor, which is bad. So I think that's about all the explanation of the circuit I'm going to give. One more thing on this. I haven't really answered the question, why is this instrument as complicated as it is? It's not checking the capacitance value. It can't tell the difference between a shorted capacitor in some situations and one that's working properly. At least not, if you're in the open position, it can't tell the difference. All it's looking for is opens. Why would you even use this instrument? Can't you just put an ohm meter or a continuity tester across the capacitor and see if it's shorted? If all you're doing is checking for opens and shorts of the capacitor, isn't that easily done? Well, I guess there's at least a couple answers to that. One is that if you did it with something like an ohm meter, now you're going to be charging the capacitor, and depending on how big the capacitor is, you might have to wait a while for it to settle in and indicate whether it's an open or a closed or shorted. The other thing is that this instrument is designed to check capacitors both in and out of circuit. So you could just have the capacitor in your hand and you clip it up and you're checking whether it's open when it should be or shorted when it shouldn't be. And you're checking to make sure it's not open and it's also not shorted. And you're doing it in circuit. So if you try doing that with an ohm meter, the ohm meter is going to respond to any DC path, and it's going to get confused very easily by other components in the circuit. But in most circuits where you're going to connect this thing up, it's actually testing the capacitor as a capacitor, not as some vaguely realized thing that may or may not conduct in some way. And therefore it is much more useful, and it allows you, again, testing a part that's in circuit with a good degree of confidence. So that's really the purpose of this instrument. One other thing is the instrument can detect intermittent capacitors, and that can be intermittent in terms of being intermittently shorted or intermittently open. And since the difference on the Magic Eye tube between a wide open and a small, which depending on whether you're in the short or the open test mean opposite things, if you have intermittency in either case, it should either flicker back and forth between the two indicator extremes or show something that looks sort of in between. It may flicker rapidly, it may just flicker when you tap it, or in other words, it may alternate between this and this if you tap it or something. So there is an indication marking on the front of the instrument that shows if you get something in between these two, or if it's switching back and forth between these two, that indicates an intermittency.